In Chapter 8 of the Basic Electricity book, we've talked a little bit about series and parallel resistance circuits, and you're probably wondering now that you know a little bit about it, how it relates to an HVAC application. And I wanted to show you that with this very common thermostat. Typically, you would call this a Trane thermostat, even though it doesn't say Trane down here at the bottom. This is the Trane thermostat, very common on VAV boxes. Zone control. Here's the thumb wheel that sets where you set the actual room set point that you want. And then you have a couple push buttons here to override night setback. So let's go over a little terminology. This is the diagram that accompanies this thermostat that we're going to look at in detail. But for now, just cover a little terminology. Right here is what's called a thermistor. A thermistor is a thermal resistor. It changes resistance as the temperature surrounding it changes. This one called RT1, resistance temperature device, 10K ohms at 25 degrees centigrade. Very common 10K thermistor. 25 degrees centigrade is also 77 degrees Fahrenheit. Right here are two push buttons. Those are the on and the cancel button. Those are normally open momentary contact push buttons. When you depress the button, it closes the contact, and when you release it, it springs back open. Here you see a fixed resistor, 1.5 K ohms or 1500 ohms. Fixed resistor does not change. Down here you see a couple variable resistors, VR3, VR1. Those variable resistor, commonly called a potentiometer, and those can vary the resistance. Right here, the resistance could vary from 0 to 200 ohms on this potentiometer, and this one here, 0 to 1,000 ohms. Moving to the next slide. This is the typical Trane VAV electronic circuit board that this zone thermostat would be connected to. This is the diagram that you would typically find in the junction box for the VAV control. And typical for Trane, instead of showing the actual connections here, they show these insets that would show whether you were using that zone sensor. The zone sensor we were looking at, the picture of the thermostat, would be this one here. There's TB 3-3, 3-2, 3-1. That refers to these terminals here, zone, ground, and set. That's where this would be connected. And if this had the communications jack, you would also have TB26 and TB25, which would be right here, which would be your plus and minus of your communications bus. But you can see here that they label this spade terminal here zone, then ground, and then set. And as we get into detail on how that thermostat sends the resistance signal to these three terminals here, you get an idea of why this is called zone temperature and set point. On the next slide, a little bigger graphic of the diagram for the thermostat, and we'll just go over this. As long as nobody is pushing the on button or the cancel button, the resistance, as you see here from temperature TB1-1, which connects to the circuit board, and in common here, the resistance between these 2 points is typically going to be somewhere around 10,000 ohms, depending on the room temperature. And you'll see a chart here on the last slide of how that'll change. But if somebody was to push the on button because they were in the building off hours and they wanted the system to start, the electronic controller would notice that the resistance, because now we have a resistance here of 0 ohms when that push button is pushed, and a resistance here of up to around 10,000 ohms, the actual resistance between TB1-1 and TB1-2 would drop to 0, because if you remember, when you put two resistances in parallel, and this resistance is actually 0 ohms in parallel with a 10,000 ohm, the total resistance of the circuit is going to be less than the lowest one. Well, you can't get much less than 0. So what you would actually see when PB1 is depressed is 0 ohms when you measure between TB1 1 and TB1 2. That indicates to the DDC system that somebody has pressed the PB1 button or turned the system into override or selected override anytime that the resistance here goes down to 0. It doesn't show that the sensor has failed. I'm sure there is a little bit of time there that it looks at that and decides that is obvious that someone had pushed the button. Now, if somebody was to push the cancel button, when you look at the circuit here, that would close and there would be 0 ohms there, but there's a fixed resistor of 1500 ohms. So the resistance that you would have when you push the cancel button is the 1500 ohms fixed resistor, and then this variable resistor again about 10,000 ohms. So when PB2 is depressed, the resistance would be somewhere less than 1500 ohms because, again, two resistors in parallel, 1500 ohm and a 10,000 ohm, the resistance is going to be less than the lowest resistance, but it's not going to be all the way down to 0. So the controller would recognize that as somewhere around 1500 ohms that somebody had pushed the cancel button. So with just these two wires, we can measure room temperature, and we can also see when somebody depresses the on button or depresses the cancel button. Down here, the two variable resistors or the potentiometers that we talked about. This one here is the actual thumb wheel itself. This is the one that sets the set point from 0 to 1,000 ohms, depending on how the wiper on the potentiometer moves across the wound coil of wire. It would change. Now, if the pointer, if you move the set point all the way to here, you would have very low resistance when you measured from common to 3. And if you move the set point way down here or the wiper way down here, you would have maximum resistance of 1,000 ohms. That's how it knows the set point, and you'll see on the chart here on the last page what the resistance between 2 and 3 should be based on the thumb wheel set point. The 200 ohm variable resistor here is for calibration. If you had the thermostat set at exactly 72 degrees, or what you thought was exactly 72 degrees by looking at the thumb wheel and the arrow pointing at the thumb wheel, and you went back to the computer screen DDC system, and you noticed that it was actually showing that the set point was 73 or 74 degrees, that's when you would go to the variable resistor here, the calibration resistor, and you would tweak it a little bit with your screwdriver. It's built inside the thermostat, and that way you could get the output or the display to show exactly the correct set point. So with this thermostat, you can calibrate the set point. You really can't recalibrate the thermistor, but in a lot of the software packages, you can have an add or subtract a little bit from the thermistor reading in the program to give a accurate temperature display. And then finally, we're going to take a look at the diagram with the temperature resistance chart shown here. Important note here at the top, it says disconnect the zone sensor from the UCM, the unit control module, or the circuit board when making the checks listed in the table below. As you saw, hopefully by now you've done the Ohm's Law interactive exercise. When you were taking a resistance reading of the water heater element, you'll notice that it was removed from the circuit. You never want to read resistance with your meter on a device when it is still wired to the system. So it's very important that when you're going to take these resistance readings between T1 and T2, or T2 and TB11 and TB12, or TB12 and TB13, that you remove the wires from the thermostat or remove them at the UCM, the module where they plug into. Here is the temperature scale, here is the thumb wheel resistance scale, and here is the thermistor resistance scale. So on the thermistor between TB1 and TB2, if you were to measure 714 ohms, excuse me, if you were to measure 15,400 ohms or 15.4 K ohms, that would be 59 degrees. If you measured exactly 10,000 ohms, 10.0 K, that would be exactly 77 degrees. So you can kind of troubleshoot that zone sensor by pulling the wires off of the sensor, measuring the resistance between 1 and 2, and with an accurate thermometer, measuring the room temperature, and you can see how closely the resistance matches up to the temperature. And for the thumb wheel set point, as you vary the thumb wheel set point, if you turned it to exactly 70 degrees, then you should read exactly 500 ohms. If it doesn't, then you could use your little calibration potentiometer here to trim with your little pocket screwdriver the exact resistance between 2 and 3 at 70 degree set point to make it 500 ohms. And of course, as you dial that thumb wheel from maximum to minimum set point, you should see a resistance change from up here, they're showing 55 degrees at 792 down to 85 degrees at 208 ohms.